In this lesson, you're going to learn how to write polynomial functions. So let's illustrate this with an example. The first one, we're told to write a polynomial function in standard form that has the following zeros. And we're told it has zeros of x equals 3, -2, and 5. So all we're doing here is working backwards from what we've previously done. We're starting with the zeros, so if you think about what the corresponding factors are, it makes it very simple to write your function. So if the 0 is +3, the corresponding factor would be x minus 3. Again, if the 0 is -2, the factor would be x plus 2, and x minus 5 would correspond to the 0 of x equals 5. And if you need a reminder of why is that, well, think about working backwards. If you were to subtract 5 from each side, you would have x minus 5 equals 0 when doing the zero product property. So this, of course, is your 0. Right? So this function, well, it is a function, but we've got to change it to standard form. So the simplest thing to do is multiply two of the binomials together first, which means you're going to quickly make 4 multiplications. That would be x squared minus 5x plus 2x minus 10. And I'll just combine my like terms in the middle there to make it x squared minus 3x minus 10. And I'm going to bring down this x minus 3 from the front. And now I need to make a total of 6 multiplications because I need to distribute x minus 3. So I begin distributing the x, gives me x to the third minus 3x squared minus 10x. And then I'm going to distribute the -3, would give me -3x squared minus or plus 9x and plus 30. Now I'm just going to combine my like terms. You can kind of see how I vertically combined or stacked my like terms like this. So you can see that my final answer here is going to be x to the third minus 6x squared minus 1x plus 30. Just a quick reminder, remember when you add and subtract, which is what you're doing when you're combining like terms, your exponents do not change. A way to check this would be graph it on your graphing calculator and make sure that it has the 3 zeros that we stated. In our second example, we're told to write a polynomial function that has x equals 0 repeated twice and positive and -2. So if x is there, or 0 is there twice, that means we would have x times x plus 2 and then x minus 2. So now we're going to multiply this together. So x times x is, of course, x squared. And I'm going to multiply the two binomials together, would give me x squared minus 2x plus 2x minus 4. So combining the like terms would give me just x squared minus 4. And then I'm going to distribute the x squared out front. So this would be x to the fourth minus 4x squared. So notice that this is a quartic function. And because it has 4 zeros, our degree is matching the number of zeros. In our third example, we have two irrational roots. We have the square root of 2, and then we have x equals -1. So I'm going to write a polynomial function. I'm calling this one g of x. So one of them will be x plus the square root of 2. The other will be x minus the square root of 2. And then x plus 1. Now, I'm going to multiply these, what we call conjugates together. I just want to remind you, conjugates are where they're identical, but one's a plus and one's a minus. And the reason I'm going to do these two is when you multiply two conjugates, your two middle terms will always drop out if you do it correctly. And I'll show you what I mean. This would give me x squared minus the square root of 2x, but then I'd have plus the square root of 2x, and then minus square root of 2 times the square root of 2 would be the square root of 4, which is just 2. And then I still have the x plus 1. So you do enough of these and you realize, well, if the two middle terms are always going to drop out, why do I even need to write them? But you need to really discover that pattern on your own. Okay, so now I'm going to distribute. I've got 4 more multiplications to make. I'm going to begin by distributing the x squared would give me x to the third plus x squared, and then I distribute the minus 2 would be minus 2x minus 1. So this gives me this cubic function for my final answer. So this brings me to the complex conjugate theorem and the irrational conjugate theorem, which really is a simple concept. It says that if a complex number is a 0, like a plus bi, then its conjugate, a minus bi, is also a 0. So they come in pairs. The same is true for the irrational conjugate theorem, meaning if I have something like a plus the square root of b, then a minus the square root of b would also be a 0. In our fourth example, we're told to write a polynomial function of least degree, and I'm going to talk about that part in just a second, that has rational coefficients, a leading coefficient of 1, and 3 and the square root of 5 as zeros. Okay, so first of all, when it says least degree, that means we're coming up with the simplest possible polynomial function. We're given 2 zeros as starting points, 3 and the square root of 5. Well, since the square root of 5 is there, I also know that the opposite of the square root of 5 has to be there as well because they come in pairs when they're irrational. So let's start by writing what our factors would be. So if a 0 is positive 3, the corresponding factor is x minus 3. And then I would have x plus root 5 and x minus root 5. So least degree is saying, okay, so I have 3 factors, I have 3 zeros. The least possible degree this function has is that it's going to be a cubic one. It is possible that maybe there are some other zeros or complex zeros that weren't mentioned. So I could possibly have a 5th degree or even a 7th degree, but we're coming up with the simplest answer. Okay, so let's multiply the two conjugates together first. And as a reminder, my two middle terms are going to drop out. So you do enough of these and hopefully you won't be writing plus 5 root x and then minus the square root of 5x. And then the square root of 5 times the square root of 5 would be the square root of 25, which is just 5. So there we go. Two middle terms drop out and I just get x squared minus 5. And then I have x minus 3 in the front. And that means I have 4 multiplications to make yet. So I'm going to begin by distributing this first. X would be x to the third minus 5x. And then I'll distribute this minus 3 would be minus 3x squared plus 15. And I am just going to restructure this so that it's truly in standard form and just verify that I have met the conditions. Okay, so my leading coefficient is 1. So this is just one possible function that has these 3 zeros. If you were told something like the leading coefficient is 2, the easiest thing to do in this scenario would be to multiply this entire function by 2. And it would still have the same zeros, and then the leading coefficient would be 2. But I'm going to just get rid of that because that's just a hypothetical. In this last one, we're going to look at having some complex zeros, which means when you look at the graph of it, you're not going to physically see it cut through the x-axis at those points. Okay, so I'm going to call this one h of x. And again, I'm told leading coefficient is 1. A 0 is positive 2, so the corresponding factor is x minus 2. And then I have negative 4i, which means positive 4i is there as well by the complex conjugate theorem. So x plus 4i and x minus 4i would be the corresponding factors. Again, I'm going to begin by multiplying my conjugates together. You will see that your middle terms drop out. So I would have minus 4i times x and then plus 4i times x minus, and then I have 4 times 4 is 16 and I times I is I squared. And if we just think for a second, what is I squared? That's negative 1, which actually means this will become a positive 16. So I'm going to have x squared plus 16 from all of that. And I'm going to bring down this x minus 2. So I have 4 more multiplications to make. So that will be x to the third plus 16x, then minus 2x squared minus 32. And my last step here will be to reorder this so it's in standard form. So x to the third minus 2x squared plus 16x minus 32.